Hi, I'm Dr. Jackie White from St. Leo University. Today we're going to discuss some counting techniques that will help us compute probabilities without listing all of the outcomes. Because in the past we've usually had to write out all the different possible outcomes. So we're going to look at some shortcuts today. So let's suppose we want to figure out the probability of winning the lottery. If you could select 6 numbers from a list of 50, well, what could we do? Let's go ahead and look at a formula that could help us with that. The probability of winning would be the number of ways to win divided by the total number of selections of 6. So you'd want to look at how many different ways are there to win, and then what are the total number of possible combinations. Well, in this case, then, since we want the probability of winning, we can think about it. We need to figure out for the numerator the total number of ways to win. Well, unfortunately, with lotteries, there's only one way to win. So the numerator is going to be a 1 because it's only one group of 6 that's actually the winning selection. But then for the denominator, we need to know how many different possible choices or different possible sequences of 6 we can come up with from 50 different numbers. That's really hard. 50 is a lot of numbers to find all the different ways you can choose 6. It could take forever. But what we can do is use some different counting methods, and that's what we're going to go over today. So the first counting method I'd like to look at is the definition for the fundamental counting rule. So here we actually have the fundamental counting rule, which says that for a sequence of 2 events in which the first event can occur in m ways and the second event can occur in n ways, the events together can occur in a total of m times n ways. Now, this isn't quite going to apply to the prior example yet, but we will get there. But this can extend to some extent because it doesn't have to be just m and n. There could be 5 different sequences that you're looking to happen, 5 different events. You can still take the product of each of them happening in a row. So it doesn't have to be just M and N. You could come on to, let's see what comes after L, M, N, O, and then P, and then Q. You could multiply all those different sequences or all those different possibilities together. Let's look at this as an example. Sometimes that helps it make a little bit more sense. So what we want to look at is, let's say the typical home alarm system has a code that consists of 4 digits. The digits are 0 through 9, and they can be repeated. And they must be entered in the correct order, though. So order is important here. Assume that you plan to gain access by trying codes until you find the correct one. How many codes are possible? Let's say we want there are 4 different numbers, 1, 2, 3, 4, that you have to enter for this correct code. How many possibilities are there for the first one? Well, 0 through 9 is 10 numbers. And there are 10, therefore, since you can repeat them, 10 numbers for the second one, 10 possibilities for the third number, and 10 different possibilities for the fourth number in the code, which gives us a total of 10,000 different possible combinations that you could find, only one of which is actually the correct code to get in with the alarm. Now, let's say we looked at this, though, and you were not allowed to repeat the numbers. Let's say you could choose 0 through 9. However, once you chose, let's say, 8, you could not choose it again. Let's look at how that would change this problem. You would still be looking at 4 different numbers. However, there are 10 different choices from 0 through 9. You could choose any of those 10. Whichever one you chose, though, is no longer a possibility. So now there are only 9 remaining choices. Now you've chosen 2 of those different numbers from 0 through 9. So there are only 8 remaining choices. And finally, if you've already chosen 3 of those numbers, there are only going to be 7 choices remaining. So in this case, if you're not allowed to repeat a number, it significantly reduces the number of possible combinations that you're looking at or the possible different orders that you could use for the code, because now you've only got 5,040. So the reason we decreased by 1 each time is because you can't repeat the numbers that were already used for this example. Now this actually can be illustrated, this reducing by 1 each time, this idea can be illustrated with something called the factorial rule. So let's pull up the factorial rule and take a look at that. What it says is that the number of ways n distinct objects can be arranged in order, and again, distinct means that they will not be repeated. That's given by n factorial, an exclamation point here, n factorial, which means take the first number n, the number of distinct objects you have, and multiply it by the next number smaller and the next number smaller, and keep decreasing it by 1, multiplying all the way down until you get to 1. So you multiply by n, and each number smaller than n, all the way down to 1. And so you read this as n factorial. Now, 0 factorial doesn't really fit into this context, so we just identify 0 factorial. That will always be equal to 1 whenever that comes up. So let's actually look at an example with a specific n value. Let's evaluate the particular example of 6 factorial. So 6 factorial, that means 6, that's the number you're starting with, times each number smaller than 6 without skipping any, all the way down to 1. So you've got 6 times 5, you multiply that out, times 4, times 3, times 2, and then times 1 to come up with a total of 720. Now that one, the multiplication wasn't too bad, but you actually, and even on a calculator, you could have done that multiplication. But when you have larger numbers or numbers like this, you can use the factorial key on your TI-83 graphing calculator. So let's go ahead. I'm going to turn on the calculator now and show you where that key is located. You'd select a 6. Then under Math, which is the first column, third row, you select that, and you've got all these choices. You use your right arrow to scroll over to Probability, and you see choice number 4. So I select number 4. Notice now that put the factorial key next to my number, and so I'm ready to press Enter. And I can see I come up with 720. Glad it agrees with the other number that I came up with, right? Because that is what 6 factorial is equal to. I did multiply correctly. It's equal to 720. How about another example? So that's just actually the symbols themselves. How about if we go ahead and look at an application of this idea? Here we have that many newspapers carry jumble. It's a puzzle in which the reader must unscramble letters to form words. For example, here you've got the letters T-A-I-S-E-R. They were included in newspapers the day that this particular exercise was written. So how many ways can these letters be arranged? Well, in this case, we've got different letters. There are no repeated letters here. All 6 of them, there are 6 letters total, that's important to notice, and they are all distinct. None of them are repeated, and so that's really convenient, and it's convenient that there's 6 because look at this. 6 of them means we're calculating 6 factorial. Now, we already looked at it, but just as a review, that's 6 times 5 times 4 times 3 times 2 times 1, and so we already saw that that results in 720. That means there are going to be 720 possible different ways to arrange the letters T-A-I-S-E-R. Now remember, that's just ways to arrange them. It doesn't mean that there are 720 words. It just means there are 720 different arrangements with these particular letters. Now sometimes order matters in certain instances, or sometimes there's different aspects, repeated letters, things like that. So let's move on to some other properties that can help us with this. We're going to look at the permutations rule next. And in this case, it's when, again, this is assuming the items are different still. We'll get to repeated items later. So assuming that you've got distinct items, then the number of ways R distinct items can be selected from N distinct available items without replacing them. That's called permutations. And so in this case, then, you've got a total of N items. You want to take them R at a time. What you're calculating out is NPR, the permutations of N items taken R at a time. And so that's the N factorial divided by N minus R. So if you know what N and R are, sorry, sounds like I'm barking, you'd have the N factorial on top, and then you'd substitute the N and the R in here, subtract it, and take that factorial on the bottom. Of course, we want to look at this in an example as well. So let's pull up an example using permutations. Here we have that the probability of winning the main lottery is 1 out of 5,245,786. So this is when the numbers can be in any order. Order doesn't matter how, as long as you have the correct numbers, you've won. Well, what if they change the rules? What is the probability of winning if the rules are changed so that not only do you have to have the correct 6 numbers from 1 to 42, but now you have to select them in the same order, so that order actually matters. So with permutations, you're looking at the idea that the order the numbers are in makes a difference. 1, 2, 3 is different from 2, 1, 3 or 3, 2, 1. So not only do you have the 6 numbers, but they have to be in the correct order. How are we going to go about solving this one? Well, whenever you think of lottery, whether they're in order or not, there's still only going to be one way to win. In this instance, you have to have the 6 correct numbers in the correct order. So the numerators stay in the same. There's just one possible way you could win. But now what we're looking at is permutations rather than combinations to get our denominator. So we've got 42 numbers to choose from, and we're still taking 6 of them. But in permutations, the order is going to matter. So what we've got is 42 factorial divided by 42 minus 6, which is 36 factorial. So here you've got 42 factorial divided by 36 factorial, and there are now going to be 3,776,000. I'm sorry, take that back. It's bigger than that. It's 3,776,965,920. So, wow, if you thought it was bad before, it's definitely a tax on people who are bad at math if you buy this lottery ticket. Okay, what are we going to do? So far, both of these examples said that the items were distinct, that you didn't have any repeated values. What are we going to do if that's not true? Let's say we've got some of the letters are repeated or some of the numbers exist in your sample. For instance, those letters T-A-I-S-E-R, what if we had two E's in there, or something repeated like that? We actually have it's still a permutations rule, but it's slightly different when some of the items are the same. So some of the letters, for instance, were the same, and like the word Mississippi, arranging those, you've got a couple of S's in there, a couple of P's, some I's, you've got repeated letters. In this case, then you'd use this rule, which says if there are n items with n sub 1 that are alike, and n sub 2 that are alike, and however many there are up to n sub k, each of these are values or items that are alike, then you'd take the total number of items factorial divided by each of the values that are repeated or each of the values that are alike with the factorial of each of those. Now, at this point, what we're going to do is go on to our final counting method, in which case the same items are not counted separately, but we do have a combination problem. So again, next we're going to go on to the final counting method that we're going to look at. And this is the case when different ordering of the same items are not counted separately. In that case, what it is a combination instead of a permutation. So let's go ahead then and look at the combinations rule. So here, the number of combinations of R different items selected from N different items, you'll notice it's very, very similar to the permutations. You've still got the N items taken R at a time. You've still got the N factorial in the numerator, and you've got the N minus R factorial in the denominator. However, when I said that 1, 2, 3 was different from 3, 2, 1 before, with the combinations, we're assuming those are the same, that they're still 1, 2, and 3, regardless of what order you put them in. So there are fewer combinations than there are permutations, so we have this extra number in our denominator, which makes our fraction smaller. That would be the additional R factorial here. So the formulas are very similar, other than in the combinations you're divided by the additional number of R factorial. Again, that's because the order doesn't matter. As long as you have the same items, that's considered one combination. So let's go ahead and illustrate this one with an example as well. A long example. Let me read the first page and we'll move on. So it says, the Pitt Software Company reduced its sales staff from 32 employees to 28. The company claimed that 4 employees were randomly selected for job termination. However, the 4 employees chosen are the 4 oldest employees among the original sales force of 32. Now, part of this is cut off, so before I read the rest, I'm going to go ahead and look at some of the information here that we might need. So what we have here is a software company that had 32 employees reduced to 28, and so that meant they eliminated 4 people, and they happened to eliminate the 4 oldest, although they say that they randomly selected the ones to eliminate. Now what we're looking for is then find the probability that when 4 employees are randomly, moving on to the next one, actually I might be able, no, we'll just get rid of it, are randomly selected from the group of 32. So find the probability that when 4 of them are randomly selected from 32, that the 4 oldest are selected. What's the chance that that would actually happen? Then after we do that, we'll say, is that probability low enough to charge that instead of using random selection, the Pitt Software Company actually fired the oldest employees? So again, they had 32. They reduced their staff to 28. But by doing so, they say they randomly reduced the staff when actually they may have. Let's see, I'm being a little critical here until we have some proof. We don't want to state otherwise, but we want to know what's the probability that the 4 oldest actually would be the ones that are randomly selected. So there's only one way for that selection to consist of the 4 oldest. So we know our numerator is 1, because either it's the 4 oldest or it's not. So there's one possibility there. And so then what we have to look at, though, is that out of the 32, how many different possible combinations of 4 are there? And so we have the 32 taken 4 at a time, and if you evaluate that, you get 35,960. So there are, out of the different ways they could select 4 individuals, there are 35,960 possible different ways they could do that. There's only one of those that consists of the 4 oldest. So maybe I had a right to be critical because that's an extremely low number. Likely they selectively chose the 4 oldest and did not use random selection here because that's a very low probability. Guess what? That's a couple of examples for us, so it means it's your turn. So what I'm going to do is put up an example for you to do, and then you can pause your video and try it. and come on back when you're ready. Turn your video back on or start it back up, and we'll go over the answer. And unfortunately, this one is also on 2 pages, but I think we can at least get the main part of the question here. Then I'll read the second part, but bring this back up so that you can work on the main part of the question. This one says that Walton Pharmaceuticals wants to test the effectiveness of a new drug that's designed to relieve allergy symptoms. The initial test will be conducted by treating 6 people chosen from a pool of 15 volunteers. If the treatment group is randomly selected, what is the probability that it consists of the 6 youngest people in the pool? So that's the main part of the question that I want you to focus on. But from there, it then says that, let's look at the remaining part. If you have a chance, you can finish this as well. It says, if the 6 youngest are selected, is there sufficient evidence to conclude that instead of being random, the selection was based on age? So after you find the probability, consider whether it seems like they actually did choose randomly or that they actually chose based on age. Let me go back to the question so you can read it again if you need to. And when you're ready, go ahead and pause your video now. Ready or not, pause your video. But when you finish, just start the video back up again, and I'll have the answer here that we can discuss. So pause your video. Remember here, we're looking for the probability of selecting the 6 youngest in this particular study. Well, there's only one way to come up with the 6 youngest. That's why our numerator is, again, 1. But then we had 15 volunteers that were taking 6 of those 15 volunteers. That's a combination. And so in this case, then we take 15, taken 6 at a time to come up with 5,005. You should have come up with 5,005 there. So that means there's one time out of every 5,005 times that you would use random selection and come up with the 6 youngest. And so in that case, that's very unlikely. Possible, but very unlikely. So it would appear that the selection was based on age, because that probability is extremely low. So hopefully you came up with 1 out of 5,005 and then recognize that that's a very, very small number. Typically, even less than 5% is a pretty slim chance. So this is significantly less than that. So very slim chance of that happening. And anyway, that actually ends our examples of these particular items. So today we discussed counting rules. That helped us define probabilities without listing all of the data out. Those rules, the different ones we looked at, were the fundamental counting rule. Then we looked at the factorial rule and used the factorial rule when we calculated the permutations rule and also the combinations rule. So I hope you have a little bit better of an understanding of these rules, and you'll want to keep working on these problems until next time.